Hello everyone and welcome to our webinar on FracaFlow, our software for fractured reservoir characterization and modeling. In today's session, we'll have an introduction to our methodology with our software FracaFlow. We would like to thank you all for attending this meeting. Today, your main speakers will be Thomas Piolet, who is a structural geologist in our consulting team, and he is also the product manager of FracaFlow, and myself, Thibaut. So I'm working currently in the sales team. Before we actually start the meeting, here are a few guidelines. So you are automatically muted, and if you have any questions during the presentation, please use the question panel and we will reply to them during the Q&A break at the end of the meeting. If we cannot address your questions during the webinar, we will answer them afterwards by email. You will also find on the right-hand side a poll panel in which we will ask you questions from time to time, so please make sure to check it during the presentation. Lastly, this meeting is recorded and we will post it as soon as possible on our YouTube channel. I will now start with the introduction to fractured reservoir characterization modeling with FracaFlow. So I will detail our methodology with this software. The fractured reservoir have a few specificities in terms of mechanism and issues. The fractures are providing permeability and well productivity. You could find extreme heterogeneity between the matrix and fractures, and you could have an early water or gas breakthrough in this type of reservoir. Also, the flow mechanisms are different than classical reservoirs, and they imply matrix and fracture. You have some challenges in characterization and modeling for naturally fractured reservoir. Indeed, the fractures are in general difficult to detect in the early production phases. It's not possible to directly measure at the well from the cores or log data the fracture network porosity and permeability. You generally have little data available for assessing the fractures, and the characterization is performed with different tools and methodology than the one you use for classical matrix reservoirs. They need a specific modeling and simulation, so a dedicated approach is required for studying this type of reservoir and accessing to simulations such as dual porosity simulation. Our software solution is called FracaFlow. It is based on more than 30 years of research by IFP Group. The IFP Group R&D specialized in modeling, so discrete fracture network, and also in simulation. This software is used daily by our consulting team and our clients for fully dedicated studies for fractured reservoirs. We have a worldwide experience in the different geological contexts, many papers that we have published and presented in international conferences. Regarding FracaFlow, the results of the software can be used in any third-party reservoir simulator, such as PumaFlow, Eclipse, VAP, CMG, or other reservoir simulator. The data from FracaFlow can be imported and exported with a direct data exchange link to Petrel. So data such as well path and logs, fracture data, the reservoir grid, which is in Eclipse format, the matrix or fracture properties, and also you could exchange seismic attributes or horizons or fault data. We have applied this software in various contexts, which includes for example, sub-seismic faults, fracture corridors, carbonate context or basement reservoirs, and also, for example, fractures in strongly deformed tight sands. How are we going to model the fractured reservoirs and proceed to a full field simulation? In order to characterize the fractured reservoirs, integration is key in the success of this type of study. The first type of data we're going to include in a conceptual model are static data for static analysis. This includes geological data. For example, the borehole imaging is a must to identify the main fracture direction and densities. You could also use fracture descriptions on core, if available, which will complement and validate the BHI observations. In addition to that, you could have outcrops of the formation or analogs that could be used in the absence of the cores or image logs. You could also use seismic data, horizons, faults, or attributes. For example, standard seismic attributes that could be used to identify sub-seismic fault lineaments. Second type of data we're going to include in our conceptual model are dynamic data. For example, well test, interference test, PLT, production test and data, mud losses, which are qualitatively used to assess the fracture influence. So not all of them are required, but the more data you have, the better it is for your study. The well test cage are generally used in the workflow for conductivity calibration. Once you have built a fracture model, you can calculate a realization of this model, which is a discrete fracture model. And from this fracture model, in which you have found the geometrical properties and distribution properties, you can calibrate this model in terms of cage using well test interpretation data. Once you have built the model, you can derive an equivalent fracture properties in terms of porosity, permeability, and block sizes or shape factor that could be used for the dynamic simulation. Different tools are available in FracaFlow for characterization of fractures. So first, you have tools for characterization of fracture from borehole imaging. The output will be fractures gathered in fracture sets with associated statistical parameters for each fracture set in terms of spatial distribution and local density. We are using borehole imaging interpretation, which are projected on 2D mode, so using a stereographic projection in a multi-well analysis. And from the resulting diagrams, we can identify different groups of similar fracture sets. And also it provides statistical information regarding the density and spatial distribution of the different fracture planes. You could also have in this kind of tool a well-by-well analysis, which is available. This is in particular used for groups of fractures or clusters of fractures and checking their location regarding the tectonic feature vicinity. In addition, you have tools for the fracture density log computation in order to understand the fracture organization. The output will be density logs, porosity logs, or fracture facies log. The methodology we use, we compute the fracture density, which is based on the fracture count parameters, and you could also apply some corrections in order to avoid some density artifacts. And in this tool, the fracturing faces are based on a user-defined stratigraphic table, which is chosen according to the fracturing degree of the faces. In particular, you could analyze the relationship between the fracture density and the faces. So you could identify a first driver of density in terms of faces. This is something you can include later on in your model. Regarding the faults, you have different tools for analyzing faults from the fault interpretation data, such as fault lineaments, polygons, or surfaces. The idea is quite the same. You're going to gather faults in fault sets with the extracted statistical parameters for each fault set in terms of length distribution, throw, fractal dimension. And in addition, you can compute some attribute maps or 3D grid properties. These properties you could use to constrain the model of faults and also generate some systematic fracture density drivers. A map viewer with multi-purpose is available in the software, so it helps to directly pick fault lineaments from, for example, a seismic property or a curvature computation. You could also compute other attributes using this map viewer, such as the elimination of slope or computing horizons, interpolation of data, and so on. You then have dedicated tools for calculating drivers in order to constrain our model. So the first tool is using a discriminant analysis in order to compute a driver that will be used in the modeling step. So you select different 3D properties of your choice, and then you're going to find correlation coefficients in order to find a combination between the fracture density log and different 3D properties. Another type of driver computation could be extracted from geomechanical constraint computation. Lastly, dynamic data, if you have such data available in your study, can be used to analyze the impact of fracture on the production. So dynamic data such as PLT, well test results, mud loss, matrix permeability logs, perforations, or production history. The idea is to understand the behavior of the fractures in terms of, and the impact in terms of production. So you could also analyze the influence of the zone of fault, or checking which wells are displaying early or late breakthrough, which is an indicator of the fracture influence. A last tool is from a characterization fracture from the stress data, so from a 1D geological data. The idea is to create different labels for critically stressed fractures. Once you have performed the different characterization in your data, you can go on and directly extract from the different tools and construct a fracture and fault model. So the idea is to create a statistical fault network model using a grid, the different set of faults and fractures, geomodel description, and this model will be a conceptual model. So you're going to define statistical parameters for your model. This is based on a discrete approach. So when you compute the DFN, which is a realization of this model, you're going to calculate for each cell a stochastic realization based on the parameters you have set and defined in your fracture set model description. So the result of one realization is a DFN, and the modeling can also be done without DFN generation. So in this case, you will only have statistical laws that will be kept in memory. Different kinds of models are available in the software, so it depends on the choice of the geologist and on his analysis regarding the tectonic context, fracture dispersion, and parameters. Once you have exported, computed your final DFN, it can be exported and used in the calibration or upscaling step. The calibration step is quite unique to FracaFlow. The objective is to tune the hydraulic parameters of fractures in order to match dynamic data, the dynamic data which is KH from well test. In your conceptual model, the geological properties are okay, but the conductivity is in general poorly known. Of course, the history match is commonly done for calibrating the conductivities, but the benefit of this methodology is to, without changing the conceptual model, so we keep a geologically representative model, we can perform a very quick multi-well calibration. This is based on the generation of a fracture model around each well and the computation of equivalent KH using analytical methods. Once the model is calibrated, you can calculate the fracture equivalent parameters and compute them. The main objective of this last step is to reduce the complexity of the actual fracture system, which is at the fracture scale, and we want to have a few relevant parameters at the reservoir simulation cell scale. We want to find the fracture porosity, tensors of permeability, and the block size parameters or shape factor in the Warren and Root representation. So for this fracture equivalent parameters computation, you have two methods available in the software. First, a numerical method, which is based on the pseudo-steady state simulation to derive permeabilities, and an analytical upscaling. In this case, the fracture network will be derived from fracture geometrical characteristics. So the last one, analytical upscaling, is based on Oda's theory. Regarding the upscaling of block size, this is based on geometrical averaging, in which you're going to calculate the mean spacing in the principal direction of flow, perpendicular direction, and height of fractures. These parameters can be combined to calculate the shape factor that you will input in your dual medium simulation. Lastly, before we go on to the software demonstration, the different FracaFlow strength in the workflow of characterization of naturally fractured reservoir is first the number and quality of analysis and characterization tools for characterization of geological data, but also characterization of dynamic data and influence on fracturing. The second strength is the flexibility of the modeling step, which can combine diffuse fractures and faults. And lastly, the step which is quite unique to FracaFlow is the calibration of the model in terms of KH. We will now go on to the software demonstration, and then we will have some time for questions.
Okay, hello everybody. So just a few words before starting, a few words about the interface. So this is actually the FracaFlow software. On the left here is a study explorer, which is where all data and analysis are accessible. And here there's a big empty space on the right used to perform the analysis, to open 3D view, log view, map view, and so on. So where all the work will be done actually. We have here also an outline which allows managing some graphical options. Of course, all windows can be reorganized. If you prefer having the data on the right, you can do it. So let's say just a few words about the case before you ask me. So this is not a real case, not exactly. Data are coming from a real case, but they have been anonymized and modified for didactic purposes. So you might think, I've never seen such a nice case, and you're probably right, but what I want here is mainly to show you the software and the underlying methods. The case is not that important here, so please don't pay too much attention to it. We have here a reservoir grid, which is mandatory for the modeling. So I open it in a 3D view. This is a small grid, 120,000 cells. It has eight layers along the z-axis. Its thickness is about 80 meters. And we have two properties inside. We have facies properties. So we have three facies actually in this grid: tight limestone, low porous limestone, and porous limestone. And we have a porosity property, which is with a strong relationship with the facies. We have also horizons available here. So I open the top horizon, so it corresponds to the top of the grid. This horizon comes from the seismic, but it can be extracted from the grid. Fault network has been picked on this horizon. It is here. So you see that I just unselect here. So you see that it corresponds to the faults that have been integrated in the grid. And we have 14 wells, which are here. Some are vertical, some other are horizontal. So you can see the trajectories here. In every well, we have a well log, fracture log, sorry. So I open it in a log view. So we have such a fracture log for every well. These fracture log come from the BHA interpretation. So you may or may not have interpreted yourself, so BHI, but in that case, you know that there is most of the time an uncertainty regarding the reality of the fractures that were picked. And this uncertainty is depending mostly on the quality of images. So you always must keep this in mind, especially if images are of bad quality. So in our case, we assume a high confidence in the interpretation, but do not forget that point. So the fracture logs are the most important data. They are the basic data for fracture study, with seismic data, of course, except that the fracture logs are rather used to analyze small-scale objects and seismic data for large-scale objects. So here we have different fractures or discontinuities. We have here in green the bedding, and in blue the open fractures. And we have this for all the logs, I remind you. We have also KH data. For example, in this well, you have here a KH value with corresponding K and H. And this KH comes, I remind you, from the well test interpretation. Okay, so I can close this now. So a FracaFlow study is usually composed of data, I just showed you, analysis, and outputs. Analysis are mostly performed through modules. These modules are accessible in the top menu here, fractures menu. So you can perform analysis, you can perform modeling, calibration, and upscaling, as Thibaut told you before. So you can access through this menu or by right-clicking in the Study Explorer. So this is the same menu. Main modules are the fracture analysis, the fracture density log computation to compute the density of fracturing, the modeling, the automated KH calibration, which is used to calibrate the conductivity of fractures, and the upscaling, of course. So let's open the fracture analysis now. So the first panel of the fracture analysis is the imported data panel, in which you drop all the wells that have a fracture log. Then, in the second panel, you have what we call a global analysis. You can see all the fractures of the field, of the wells. So all available data at wells are seen on this interface. So the purpose of the fracture analysis is to assess the main orientation and the distribution of fractures throughout the field, and to discriminate the fractures into groups. So sometimes I will say fracture sets or fracture families, but this is the same. There are basically two kinds of organization: in clusters, characterized by a high density of parallel fractures in a narrow interval, or diffuse, characterized by definition by the presence over the whole field. So usually, after a quick look over the general orientation of fractures in this interface, we start by the well-by-well analysis. So you must open every well in separate clusters from the background of fracturing. So let's open the well 40. So the interface is very similar, except that you have a log view, which is integrated. So what we are looking for here is peaks in the fracture density curve, which is displayed in this track here. So here, for example, we have a peak. So let's zoom in at this peak and select the fractures. So you see that on the stereodiagram, poles are the orientation of fractures actually are very, there is a lot of dispersion. You have all orientation. So this does not correspond to the definition of a cluster. I remind you that a cluster is composed of parallel fractures in a narrow interval. So it is not a cluster. Let's see the second peak at the bottom here. We select the fractures, and you see that this is the same. Actually, this peak can be explained by the presence of a facies change, a facies variation. So we do not have any cluster probably in this well. So let's try the other one, the well 42. So you can see two peaks here. Let's zoom. And here I select. And you see that this is really different. We have only one orientation. So here we can say, yes, this is a cluster. We have parallel fractures and in a narrow interval, so with a high density at this depth. So we can create a cluster. And later on in the modeling phase, we will probably model this cluster as a linear mount. So you should normally do that for all the wells to analyze all the wells and detect all clusters. Then you go back to the global analysis interface and try to discriminate the remaining fractures in terms of orientation. So we have here the stereo diagram, which is very useful for this task. And we have this option, density. I click on this one. And what is this option? This is the density of poles on the stereo diagram. And what you see is that you have two principal orientations, which are visible. And we have in this fracture analysis an automatic gathering which is based on the density of poles on the stereo diagram. So if I click on this button, automatic gathering, the fractures are automatically discriminated into 3 groups. It could be more, but 3 groups is fine. So you have the 2 groups, the blue and the green, which were visible with the density view. And we have a third groups in purple. So the orientations are north 70, north 120, and north 10. Okay, so we have here 3 diffuse fracture sets that we can save in the fracture in the study explorer. So here I have my 3 sets, north 70, north 120, and north south. Of course, the analysis should maybe not be so quick. You should cross-check the data, see that all orientation exists in all wells, see the relationships with the faults or any other properties, and so on. But let's assume the analysis is correct. So let's close the analysis for now. Then we want to compute the density of each set. So this is the fracture density log computation module. The input is my one set. Here, this is the north 70 set, and all the wells, because all the fracture logs are in this contained by the wells. In the second panel, you can manage, you can change different parameters for the calculation, for the density calculation. We generally integrate a Terzaghi correction to this calculation. And this correction takes into account the angle of the fracture with the well bore. Indeed, the fracture set density has to be computed perpendicularly to the fracture plane's orientation. The results are shown in the analyze facies control. So here you see the table at the bottom. So we have 3 flashes, and the density of fracturing for this set, so the north 70 set. So this is a mean density. And you you will do that for all the sets. So north 70, north 120, and north 10. Then you can switch to the fracture modeling. So at this step, maybe the analysis is not fully completed, but we can build a model. So in this model, basically, what is the modeling? It consists in describing what has been analyzed in the previous steps. Creating a model is to define a few parameters for each family that has been observed: orientation, density, length, aperture, and conductivity. Orientation and density have been deduced from previous analysis, fracture analysis and fracture density log computation. The length is a parameter which is very difficult to assess, and we use most of the time values from the literature. Aperture is usually deduced from the conductivity through the Poiseuille's law, and the conductivity is assessed during the calibration steps that we will see afterwards. So here, this is a fracture modeling interface. In this window here, we will create all the families, all the fracture families. And when I say fracture families, this is diffuse fracture families, fault families, and so on. So we've seen that we have 3 diffuse fracture whose density depends on the facies. So we have 3 facies-based model, 1 per orientation: north 17, north 10, north-south, and north 120. I have a fault set, and I have, this is just to show you, because we haven't performed any analysis for this, but this is a fault-related fracture model. So fractures will be generated along the faults. So let's just open a set just to see what it looks like, what kind of parameters you have to specify. So you have several sections. The first section is the orientation, and the orientation will be retrieved from the set. So this is a real orientation. The real orientation, mean orientation, will be computed at well and interpolated in the rest of the field. You have a section for the size. So as I said, we mostly use values from the literature. Here, the aperture, so we use the default value, and it will be changed later. The conductivity, again, a default value, but that will be calibrated during the calibration step. And finally, the spatial distribution, which corresponds to the density. So 1 density for each facies. Then you can compute DFN. So the DFN, or 3D representation of the fracture model, is generally generated in a small area. So I will show you. So the purpose of the DFN is to validate its definition. The calibration and the upscaling are indeed based on the model definition, not on the 3D representation. So you must understand that the algorithm that follows the calibration and upscaling do not use the 3D representation of the fractures, but only its definition, which allows to to handle billions of fractures actually. So this is the DFN. So you perfectly see the faults, of course. And regarding the different fracture set, we have the fractures. I just zoom a little bit more. Fractures oriented north-south, fractures oriented north 70, north 120, and the fault-related fractures. Okay, so we can close now the modeling and switch to the calibration step. So we've reached that step by considering geometric or static aspects. And you know that the dynamic data are at least equally important. Indeed, what is the purpose of building a nice and realistic model if the fractures have no impact on the production? The calibration module, the automated calibration, the automated cage calibration is a multi-well calibration. So you can see here all the wells having a cage interpreted. You have to define here in the radius column the drainage area. Then when you go to the second panel, you have to choose the parameters to optimize, and the main parameters is the conductivity, of course, and you define a range for each set. So the principle of the algorithm is to find within this defined range of conductivity, which can be, of course, different for all the sets, the values that allows best fitting the cage observed at wells. Then if you go to the computation settings, you specify the matrix permeability, and then you click compute. But there are different strategies to reach a well-optimized model. It is not just a click button black box. I have no real time for long explanations, but here we usually calibrate the sets one by one. So you can make assumptions. For example, the conductivity is assumed to be greater than that that overset because of the stress direction, and so on. So you usually run several calibrations before getting the final conductivities. The results can be seen here. So you see in the first column the interpreted KH, and in the second column the simulated KH using the optimized conductivity. So this is the best conductivity for all the sets. So you save, you export or save the model. So this is exactly the same model than the one you built in the fracture modeling, except that the conductivities have been updated, calibrated. You're supposed to modify the aperture then with the Poiseuille's law, and then you can switch to the upscaling part. The upscaling is the last step of the workflow. So what we call upscaling is the computation of the fracture network equivalent properties. The analytical upscaling is based on Oda's formulation. So this is a paper you can find in the literature. It dates back to the 80s, I think. So this upscaling can be run using the single or dual media hypothesis. The computed properties are the permeability along the three axes, the porosity, and the block sizes or shape factor for the dual media case. So I can show you the upscaling corresponding to this model we just built. So here I have the block sizes and shape factor, and here the permeabilities. So let's open, for example, the permeability along I-axis in a 3D view. Okay, so you see, and this is not a surprise, that the permeabilities are depending on the facies, of course, or diffuse fracture set depends on the facies. And you also can see the faults and the corridor around. And here, just for the example, the shape factor. The final step is the export. The properties are exported for the dynamic simulation. They can be used in any simulation software, like, of course, or in-house software, PlumaFlow. So this is the end of the demonstration. Just another detail which was to be noted. The example today is using a small grid, but you know that grids are every day bigger. So now it's very common to have grids with tens of millions of cells. So for this, we have adapted our software, and the upscaling can be run using several processors. Okay, so this is now time for the Q&A sessions.
So the first question is, in your workflow, how do you calibrate the well information in terms of logs, tests, cores with 3D seismic volumes or facies volumes? Is it a statistical propagation between the wells? Actually, this is how related to how we construct our model. In our model, we're going to construct statistical laws for the different fracture sets. So this is not a propagation between wells, but the idea is to fill the reservoir grid with different sets in which you have defined different statistical laws in terms of density and size of fractures. So it is possible indeed to constrain, for example, the density of fractures with some seismic 3D volumes. In this case, you will add your seismic volume as a constraint when you define the statistical law in your model. Second question, can you give some advices for choosing the sampling rate, low and high frequency windows for the fracture analysis when working with horizontal wells?
Well, it depends really on the case, if you have a lot of fractures or if you have few fractures. So usually I use a calculation window, which is at least the spacing between two fractures. And for the sampling, you can take half of the window. But you have to try several parameters. I cannot say use 10 meters for horizontal wells and 5 meters for vertical wells. It depends on the case.
Another question is, do you need a fault interpretation as an input, or can you use seismic attributes that respond to discontinuities?
You are not compelled to import fault interpretation, but you can use a seismic attribute to pick the faults in FracaFlow. So, for example, a curvature map or coherency map or any relevant seismic attribute. If the idea is to model faults, then you need to pick the faults or to import a fault network. If the idea is to constrain the fractures related to faults, then you can, of course, as Thibaut told you, use fault seismic attributes.
And another question which is in the same subject: can you control spatial distribution, so generally intensity, with a seismic attribute? Yes. So yes, you can control with a 3D seismic attribute or an attribute in the imported as a map and constrain the density in one of your fracture model. If you have any other question, please contact us via email. We'll be glad to answer you. So thank you very much for attending this webinar, and see you soon in another webinar.